Hi guys, my name is Cavicchia and I run a little website called Cavicchia. This is my first video publishing, and this video we're going to take a look at the AP Physics 1 free response questions, specifically from the 2016 administration of the exam, and we're going to start off in this kind of series of videos with question number 1. So if you want to look at how to solve a wheel rolling down a ramp kind of problem, keep watching. So for this kind of problem, we're given this scenario where we have this wheel. It's got like spokes on it. And this wheel is rolling down this ramp. And it's not floating. Let's kind of pretend that it's actually touching the ramp there. This ramp makes some angle theta, and it tells us that this wheel has a mass m, makes an angle theta, and it is rolling to where the ramp exerts a force of static friction on the wheel, so the wheel rolls without slipping. So the rolling without slipping, basically that's kind of the extent of what we'll do in AP Physics 1. We won't really get into slipping. We need a little bit heftier analysis than what we do in this course. But part A is taking a look at the forces acting on the wheel as it's rolling. So for part A1, we're asked on the diagram below, and it gives us a little diagram, kind of the same thing as the picture. Here's our wheel. There's the wheel center-ish, kind of center-ish on my drawing. And it gives us the ramp. And it says, on the diagram below, draw and label the forces, not components, that act on the wheel as it rolls down the ramp. And it's asking us to do a couple of specific things. Draw an arrow starting on and pointing away from the point at which the force is exerted. And it also tells us that we don't need to worry about the lengths of our arrows. So, the forces acting on this wheel. I'm going to make my center a little bigger just to cheat. The forces acting on my wheel as it's rolling. Well, force we always have on any object on Earth is going to be the force of gravity. And the force of gravity we know points straight down towards the center of the Earth. But where does the force of gravity act from? Like, where do we start the force of gravity? Do we start on the bottom, top of the object? And the answer is your force of gravity, we can kind of assume to act from the center of mass of an object. So the force of gravity is going to go from the center of the wheel. And a lot of people want to do everything kind of as a dot down here. But we want to make sure that we're doing our forces from the appropriate points. So this wheel is resting on a ramp. It's resting on a surface. And anytime you have an object that rests on a surface, you're also going to have a normal force. And the word normal means perpendicular in math and physics. So a lot of times you want to just make the normal force go opposite the force of gravity. And if this was on a horizontal table, maybe that'd be true. But in this case, a normal force is at an angle because our ramp is at an angle. So our normal force is going to go perpendicular to the ramp. And the normal force happens because of the surface. So the normal force, oh, I accidentally erased my wheel there. Let's get him back real quick. He's an orange now. The normal force happens because of the surface. So the normal force is going to start on the surface and then go perpendicular to the surface. And it should pass like reasonably through the center of that wheel. Now, the normal force, you can label Fn, and the force of gravity, you kind of label that W for weight, mg, whatever you think someone will understand, or if you're not sure, you could always write out the whole word or make like a little key for like what means what on your diagram. So we have one more force, and this force tells us in the problem that the wheel has static friction. And friction always acts in the opposite direction to where your object is moving. So our static friction is going to start again on the surface and then go opposite to the direction that our object is moving. And there is part A. So let's take a look at part A. Well, it's part A1. Let's look at part A2. In part A2, we're going to do a little explaining. It asks us, as the wheel rolls down the ramp, which force causes a change in the angular velocity of the wheel with respect to its center of mass? So we're going to need the help of our diagram for a second, because why do objects change velocity? Acceleration. And why do objects have acceleration? Force. And we're talking about angular velocity, so we're talking about angular acceleration and angular force. So an angular force will change our velocity. And what is the angular equivalent of force? Torque. Do you remember how to find torque? It's force times radius. And I like to put a little perpendicular sign in here on either the F or the R to remember that they have to be perpendicular to each other. So, which force acts perpendicular to the center of mass? Well, the force of gravity goes through the center of mass. The normal force also should go through the center of mass, but friction does not. So friction has to be our answer. It is the only force that is at a distance from the center of mass. And then we would put in there maybe that it produces a torque. So I'm going off the page for a sec. But it produces a torque, and that is the important part here. It produces a net torque on the object because of a non-zero radius. I like to make sure my students know that we should refer back to an equation. So torque equals force times radius, so we shouldn't speak too generally in a free response question. Refer back to an equation or a principle or something. So in my explanation, I'll probably need to refer to this equation. And there is part A. So let's look at part B. Part B, we're going to do a little calculation. Part B says, for this ramp angle, the force of friction on the wheel is less than the maximum possible static friction. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite the force of friction. I don't know what that means yet. I'm just going to write it down. So the force of friction is 40% of the force opposite. I don't know what that means yet. We'll figure it out. So it asks us to derive an expression. Derive an expression means we're going to have to have a symbolic answer probably for the linear acceleration of the wheel. Okay, so we're looking for the acceleration of the wheel. And this is one of the most important parts of this, is it tells us some key terms. It says, in terms of. So in terms of means the variables we're allowed to have in our final answer. What variables are we allowed to have? Well, the problem says m, theta, and constants. Mass, angle, numbers like g, big G, Coulomb's constant K, permittivity, something that is like a set value on our equation sheet. That's it. That's what we can have. By the way, did I already say this? Linking to the actual question below from College Board, so you can refer to the actual question and not just me reading it to you. But we're looking for acceleration. We just did something about forces, so that should be a key to you that we're using forces to find acceleration, or we're going to use our equation known as Newton's second law, which usually we see written as F equals ma. Our equation sheet puts it as A equals F over m. I like that because it's kind of a cause-effect relationship. But one of those two. We're going to be doing some on the forces. We have a forces question, probably going to be doing some of the forces. So let's take a look back at our free body diagram real quick. In which direction does the object accelerate? It accelerates in the down the ramp direction. So we're going to be summing the forces in the down the ramp direction. I'm going to add some force components to my free body diagram. On my actual answer, I'm not going to do that. I'm going to make sure I do not have force components on that diagram. But I'm going to draw myself a second little reference free body diagram to kind of figure out what forces are acting in my down the ramp direction, because I'm summing the forces in that direction. So let's just real quick draw a little free body diagram kind of similar to what we did up there. So we had the force of gravity, we had the normal force, and we had the force of friction. Maybe I'm going to simplify this for a second, just like pretend that that wheel is a dot, just for the calculation part to make it a little easier to visualize. And our normal force is already kind of on our axes. When we have an object on a ramp, it's helpful to make your axes considered the down the ramp and perpendicular to the ramp directions. So the normal force is on our y-axis. The force of friction is on our x-axis. What force do we need to break into components? That's going to be the force of gravity. We're going to have an FGY and an FGX. And this ramp, it makes an angle that is equal to the angle that we have up here. Why is it equal to that angle? Well, this is a statement that is usually, obviously almost always true for our objects going on a ramp. The angle the force of gravity makes with the y-axis is equal to the angle of the ramp. We can do some geometry, maybe another video on kind of why that exists, but if you have trouble with that, draw out your angles, do some alternate interior angles, kind of geometry it out. So we're going to sum our forces in what I call the x direction, or the along the ramp direction. What forces act in our along the ramp direction? I'll move over here. Well, going down the ramp, we have FGX. Going up the ramp, so in the negative direction, we have FS. Now when we take the sum of the forces, we're going to use Newton's second law. That equals MA. So what is FGX? Well, the force of gravity is equal to mg, just the x component. So my x component here is opposite of the angle. Sine is opposite, so we're going to use sine theta. A lot of times for x, we always want to use cosine. Make sure we're paying attention to the geometry of the problem. And this is, well, I'll write this here, but we're going to kind of rewrite this, because I'm going to think back to what the problem told me. The problem told me that the force of friction is 40% of whatever the force is opposited. What force is opposite of the force of friction? And that's our FGX. So we can rewrite this. mg sine theta minus the force of friction is 40% mg sine theta. So I'm going to write 0.4 mg sine theta equals ma, and we're almost done with part B. I can divide the whole equation by mass because there is mass in every term. It cancels out. Then I'm left with g sine theta equals 0.4 g sine theta. So this is kind of like having 1 g sine theta minus 0.4. What is 1 minus 0.4? 0.6 g sine theta equals A. Boom. We're done. Now, I always like to tell my students to look back at their in terms of what were we allowed to have in our equation in terms of m, theta, constants. Well, we didn't need m canceled out, but even if we left m in there, that would be okay. G is a constant, and then theta, and then that's the only actual variables of the equation. So we're good. There's part B. Remember, Freebody diagram, sum of the forces, simplify. That's our general kind of steps for any sort of forces problem. We have to solve for something. Last part, part C. In a second experiment on the same ramp, a block of ice is released from rest, block of ice of mass m, so same mass as the wheel, is released from rest at the same instant the wheel is released. So we have a little race between a block and a wheel. The block slides down with negligible friction, which reaches the bottom with the greatest speed. So I love this when this question came up on the national because we do a little lab kind of similar to this in my class. So basically we have two scenarios. Pretend these are the same ramp. My picture doesn't look very same, but we have a block and we have our wheel, and they're both the same mass. And we're looking for speed at bottom. Which one has a greater speed at the bottom? And we could solve for that speed. I'm not going to solve for it. Maybe we'll do another problem to solve for it. We'll do a little bit of solving. But we're just asked conceptually which one's faster. And how do we judge which one's faster? Well, this problem asks us to do it two ways. We're going to do it in part C1 in terms of forces, and part C2 in terms of energy. And the nice thing is, we already did it in terms of forces. We got an acceleration of 0.6 g sine theta for the wheel. The block wouldn't have that 0.6 because it wouldn't have this minus 0.4 part of it. The block is just g sine theta. Because it experiences no friction. And then we can refer back to our answer from part B. We said a wheel is only 0.6 g sine theta. So if you have less acceleration, can I rewrite that? You will have less final velocity. Therefore, block wins. And this is one of those kind of one-point statements, so don't write a whole paragraph or something like this. But we can state it kind of simply that because you don't even have to use the equations I used. You can say that the block experiences no force of friction, which will lead it to have a greater acceleration or a larger net force, which will therefore make it have a larger final velocity at the bottom of the ramp. So we kind of already did that in part B. The last part is doing this in terms of energy. And in terms of energy, we can explain it using our types of kinetic energy. So before I kind of look at our explanation, let's think about what type of energy they have. They're both starting at the top of the same ramp. So our block and our wheel both start with all of their initial energy is gravitational potential energy. For the block slides down, no friction, no thermal energy. So when it gets to the bottom, all of that energy is kinetic. And specifically, it's translational kinetic. So if we wanted to solve this, we could then solve for the velocity in terms of that initial height that it was given, and we could square root 2gh. For the wheel, the wheel not only slides down, so it has translational kinetic, it's rolling down, so it has rotational kinetic. And that rotational kinetic takes away from its final velocity. If we wanted to write that out in an equation, we could. Remember, rotational is 1/2 I omega squared. We could simplify this further. If we were solving numerically, I for a wheel is, if we're modeling it as a hoop, mr squared, omega is v squared over r squared. And we can kind of then look at, okay, 1/2 plus 1/2 is only 1/4. So we're going to end up with less final velocity. We solve this numerically. Not numerically, we can talk about the forms of energies conceptually. They start with the same gravitational potential energy. All of that block's potential energy becomes translational kinetic. The wheel has to split that energy up between translational and rotational kinetic, which takes away from its final velocity. Or you can think about that it takes energy to make it rotate, so it has less energy to move translationally. And there it is, we're done. There was our AP Physics 1 free response question, number 1 from the 2016 exam. As I said, I'm going to link to the actual document below. The College Board website also has student sample responses and tips from the graders and all sorts of cool information that I think you should check out. I'll link to it below. But I hope you understood this explanation. Hope it was a good first video. If you have any questions about it, you can message me, leave it in the comments. I'll try to answer them. Thanks for watching.